Buffering here. All right, so we're going to start up around page 84, 85, 86. Let me get this buffering stopped. All right, there we go. And let me just do a quick summary. That way we know what we're doing today. A couple markers here. All right. Our goal today is to do conservation of angular momentum problems. And let me just give you a quick flow chart for the reasoning, the rationale you might have in your brain as you're trying to do these. So first step, it's a lot like the chapter 9 strategy. First, we need to verify it's okay to use that. And by that I mean, is torque external net, kind of sloppy, is the sum of external torques approximately equal to 0? Or is collision time so short, the sum of torques is negligible? Somewhere in there, something like that. Basically, we need to have no external torque, or we need to have a system in which the collision time is short so that even if there is an external torque, it acts for a negligible amount of time. All right, not happy with that marker either. That's better. Usually we draw a before and an after picture, so maybe that would look something like this. And then this would be before, and then after might look something like this. When they hit, you draw the center of mass, and it's rotating about the center of mass. So there's an omega, and maybe it's even translating to. So there could be a V final and an omega final. Something like this, where we draw, remember how we drew before and after pictures for chapter 9 problems? Same kind of deal. Or it could be something that looks like this. There's two objects. One of them is rotating, and maybe you drop another object on top of it. We're going to do this one in a minute. You don't need to draw this crap, but I'm just trying to give you an idea. Maybe you drop them, and then they're rotating together. So imagine you drop something onto a rotating object, right? When you do that, maybe the combined object will rotate at a different rate. This might look like an omega final or an omega initial. Basically, we're going to have before and after pictures. But remember, because it's angular momentum, usually there's some sort of omega involved. So it's, yeah, we'll see pictures that look a lot like this kind of stuff. You don't need to draw this out, right? Because we're going to do these actual problems in a minute. Okay, that's cool. We could use some equation that looks like this. And then, as always, we're going to be careful with plus or minus signs. And with the case of point mass, if you have a point mass moving in a straight line, replace I omega with M V R perpendicular. We talked about this last time a little bit. Does anybody remember what R perpendicular means for a angular momentum problem? We had another name for it. It was a parameter. Impact parameter. Do you remember me saying that last time? I don't know if you do or not. Sometimes we're going to call this R perpendicular a thing called the impact parameter. Just to keep it straight from a lever arm for a torque problem. That's all. It has its own name because it's to the line of motion, not to the line of force or line of action. This is basically your strategy for doing conservation of angular momentum problems. Remember, the whole point last time was we talked about angular momentum. We learned how its units work and things like that. We learned how to figure out an impact parameter. And now we want to actually use the concept of conservation of angular momentum. We want to use this concept to analyze problems and figure out perhaps its moment of inertia or its initial rotation rate or its final rotation rate, some parameter. We're going to know some of this information and use this principle to figure out other pieces of information. That's it. So far, so good? Should we try one? I'll try to leave this up here for a minute. Hey, let's go to page 86. Let's do it. If you look at the top of page 86, that's kind of a short summary of this, right? Notice the tricky part is going to be point masses. Point masses are always being treated differently. And so at the top of page 86, I summarized the tricks for point masses. You see that special note on there? You got it? Everybody got it? Okay. And I'm going to try 11.5. I'm going to switch over here to this board. We're going to look at 11.5 together. And while you're reading that, maybe I'll get the simulation here. Oh. There it is. Take a look. You got a turntable, it's spinning. You drop this on there. Did you notice the rotation rate changed a little bit? Let's do it again. Watch this rotation rate, the RPMs. When I drop this on there, do you agree it slows down a little bit? We're analyzing this problem, and we can try and say, okay, if you put these two objects together, what's the change in rotation rate? That's it. Got it? Okay, let's put the problem up on the board. Okay. So initially, call this before, you could call it stage one, you could call it initial and final. There's a large metal disc. So we're going to have a disc. Do we know any properties of that disc? Mass M. Radius R. And then we're going to use a thin ring. Right, so this is supposed to be the thin ring here. Sorry if that doesn't visualize it very well. So the thin ring has mass the same and the same radius, I believe, right? Identical mass and radius. Okay. Now, initially, this thing is rotating down here. Disk initially rotating. All right. And I'll say omega initial equals 10.0 RPM. So you probably don't need the S on it, but we always say RPMs, but really it's revolutions per minute, right? So 10, right? You don't need an S on the end, but it's sort of like pounds versus pounds. You don't use the S at the end of LB. All right. Okay. Afterwards, we drop it on top of here. So they're both sitting on top of here. Supposed to be the same exact radius. That's pretty close. Sorry, it's not perfect. Put that axis in here. They're going to rotate together with some final rate. I'll call that omega final. Now, if we want to use angular momentum, what's the first step that I said? We should do what? See if it's reasonable to use it. Now, in this case, when you drop this thing on here, maybe I'll bring it up to here so we can look at it again. What are the forces involved when I drop this thing on here, right? When I drop this thing on here, what's one force acting on the ring?
Gravity.
Gravity. Is that going to cause a torque about this axis? The gravity is going this way, right? It's bound. We don't have to worry about a torque due to gravity. Sweet. What other force is present?
Normal.
Is that going to cause a torque about this axis?
No.
Is pushing up this way going to change the rotation rate of these? No. Anything else?
Friction.
Friction. Where does the friction occur?
Between them on that.
You can hear it, right? Is that going to cause a torque?
Yes.
Yes. Is it external?
No.
It's between the two, so it's internal, and that's the torque, which causes the change in rotation rate. Yes, there's friction between them. Yes, that friction causes a torque, but it's not external. So is it okay to use conservation of angular momentum in this case? Yes. Okay, so I will just mention that friction causes internal torque. Okay to use L initial equals L final. Now in this case, to simplify this, maybe we should draw a full coordinate system. I'm going to call this X and this Y. So what direction would this be? Positive Z or negative Z? X goes to Y. What is that? I hat, J hat, K hat, positive Z. Oh, thank you. Thank you, Jules. Sorry about that. Let me do that again. I chose to call this the positive X direction, this the positive Y, and this the positive Z, right? X goes to Y goes to Z. X, Y, Z, I, J, K. Sorry about that, Zoomers. Now this thing's rotating around here. What direction is the rotation? what do we say this direction is? Positive k hat. All right, now, why am I mentioning that? We can use that for this vector here if we need it. So in this case, let's write it out. I1 omega 1 initial plus I2 omega 2 initial equals, how many objects do we have in the final state? We could view it as just one with moment of inertia I1 plus I2, sort of like a perfectly inelastic linear momentum. Does that make sense? The total moment of inertia times omega final. I want to pause. Is everybody good with that line? That makes sense? Over there, you're good? Robert, you're good too? Okay. So then at this point, what thing is equal to 0 in this equation? Something's equal to 0. One of the terms in here is 0.
The second term?
Which term? This one?
Yeah.
Why? Yeah, initially, this one was not rotating. So we could say omega 2 initial was equal to 0. It was not rotating before the collision. Does everybody see that? So it's a lot like your normal momentum problems. That drops out. What is I1? What shape is it? A disk. So what's the equation for I1 for a disk that has this mass and this radius about this axis? Is it 1/4 or 1/2? 1/2. And then we know omega 1 initial. Maybe I'll label this omega 1 initial right here. Slipped in a 1 because we chose to call this one 2 based off what somebody said. Well, there's a 1/2 mr squared there. What's the moment of inertia of object 2? It's a thin ring, mass m, radius r. What's that going to be? Just mr squared. All the mass is distance r away, just like a point mass. It's like a weird point mass. What's going to drop out? And? Yeah, and what else? Both the m and the r. Do you see every term has an mr squared in it? So now, rewriting this, we get this is going to be 1 plus 1/2, that's 3/2. Notice, what is omega final in terms of omega 1 initial? 1/3. Let me see what we were supposed to do. Ah! Okay. Oops. I was going to have you guess what this should be, but take a look. Does this seem reasonable with what we saw in real life? The final rotation rate is 1/3 of the initial. We saw it slow down, right? Now, in this case, if the demo that I did wasn't exactly the right masses and radii to make this match perfectly, but it gives you an idea here. We do expect it to slow down. In this case, if we have these exact parameters, it would slow down. You'd lose 67% of your RPMs, all right? In this case, wait, we talked about this. There was something else I was going to say here. Oh, we didn't get the velocity in radians per second, but I want to point something out here. this is a cool procedure. By doing the problem algebraically, when we work this all the way out, do you agree I could convert or I could not convert and I would still be able to use this equation? So this is one of the equations where we wouldn't have to out-convert from RPM to radians per second. This equation is valid for either set of units. Not all of these are. In general, to be safe, you should always use radians per second on a test. But here we see you wouldn't need to. That's what I wanted to point out. Yes.
Yes, angular momentum independent of linear momentum.
So in a lot of problems, they're involved together, but you can do a linear problem completely independent of an angular problem. Is that what you were asking?
Yeah.
In fact, was linear momentum conserved here?
Oh no, because the collision sound.
So it depends on what you call the, right? Initially, if they're both sitting here, negligible distance apart, what's the momentum in the y direction up and down here? How much are these things moving up and down? If they're really close together and I haven't moved them yet, and they're not moving, right?
Yeah, so zero.
So there'd be zero. Now, true, when I let go of this, it starts to fall down. There you could argue, oh, conservation of linear momentum is not valid because the Earth made this object accelerate, right? So, but if they're basically almost in contact, you could even argue that there was negligible momentum initially vertically and negligible momentum vertically afterwards. So in that sense, you could also argue conservation of linear momentum is also valid. 0 equals 0, so to speak. Is that good enough?
Yeah.
Yeah. And we're going to do problems where they're mixed in a minute. Good enough?
Yeah.
All right. Let's see. What do we want to do with this? Okay. Convert to radians per second. Let's do that. Just because I'm pretty sure I did that on your test in some question to make sure you could do that conversion. So even though I didn't do that initially, let's do that conversion real quick. So if you did need to convert, you could use that conversion. Hopefully you're okay with that. So you could do this conversion either before or after you did the angular momentum calculation. Oh, here's a fun one. What should happen to the energy? Okay. Do you think the amount of energy goes up, down, or remains the same? Why do you say down?
Lost momentum.
True, but you gain moment of inertia, right?
Oh, isn't it because it's an elastic point? No.
This is a perfectly inelastic collision. What usually happens in a perfectly inelastic collision? Do you gain energy, lose energy, or does it stay the same? If somebody punches their fist into my face and it becomes part of my face, do you think I would gain energy, lose energy, or, well, do you think the system would? Maybe that's a bad example. Two cars crash together, right? They usually lose energy when you have a collision, right? Most collisions, you lose energy. Perfectly inelastic, we always expect to lose energy. But there's no internal torque. What's the deal here? Remember, for energy to be conserved, what has to be true? What's our energy equation? E initial plus work equals E final, right? It's possible you could have negligible torque, but you could have some work done and the energy could change. Now, in this case, what's going to happen is the friction is going to cause these molecules to heat up when it's during the collision, right? And so we're going to lose some energy from macroscopic kinetic energy to internal energy of the molecule. So we're going to lose some energy. All right. I'm running out of room. I want to do it right there. Forward placement's tricky here. So if I want to talk about the change in energy, right? Let's say we wanted to figure out the percent delta K. Well, that's going to be K final minus K initial all over K initial times 100%, right? In this case, we can actually work this out. K final would be 1/2 I final omega final squared. And there's the reason we're going to get the change. The moment of inertia goes up, but the RPMs go down, and that term is squared. So that's why the decrease dominates. Now remember, kinetic energy has a 1/2 times I. In this problem, I initial also has a 1/2. All right, so you got to really watch the 1/2s when you're doing these. Also, notice the following. This is probably one of the more common mistakes in this class. Students will accidentally square an omega here, right? But look at these equations. They're so similar. Energy is I omega squared with a 1/2. Angular momentum is just I omega without the 1/2, without the square. No 2's in angular momentum. Got it? You've got to watch that. Also, notice how important it is. I know this seems silly, but a lot of students will try to do this problem with rotational energy. You know it loses energy because I've just told you that. So people that try and do this problem with E initial equals E final get it wrong every time and get 0 credit. I don't give any credit for somebody that uses energy on an angular momentum problem. I just refuse. I can't stand it. So you've got to know if you have a collision with rotation, angular momentum. If you have a collision with rotation, do angular momentum, not energy. Got it? Just keep that in your gut there. Now we can come over here and clean this up, right? In this case, when I plug this in, I final is what? 3/2 mr squared. Omega final squared is going to be 1/9 omega initial squared. Take a second. Omega final squared is 1/9 omega initial squared minus 1/2 mr squared times omega 1 initial squared. What drops out in this ugly mess? Tell me one thing that drops out. What is one thing that appears in every single term?
Omega initial.
Omega initial drops out. I heard radius drops out. What else? Mass. Isn't that amazing? Here's another reason we do these problems algebraically, right? We can see that the mass, radius, and the initial rotation rate won't affect the percent energy loss. Interesting. So now the 2 also drops. Do you see that? There's a 2 in the basement of every term. That's getting so messy, but what is that? 3/9, that's 1/3 minus 1. Well, that's -2/3 or -67%. I think I'm just off. The idea here is if you plug in all the numbers on this, it turns out this seems very similar to chapter 9. Gee, we triple the rotational mass and I lose 2/3 of my energy. If you go back and look at the other calculations, they would be in chapter 9, they would act exactly the same way. I don't know, did I lose you here or did this make any sense? Or how are you feeling? Thumbs up, thumbs down. Good, sideways. Gonna need to do a couple more maybe. All right. I'd like to say we're done with that problem unless you have questions about it.
Is there also for 1 on 2?
Yeah. So, I mean, to be fair here, let's go back to this. Sometimes the objects actually help. I'm going to call this the disk and this the ring, okay? So we got disk and we got ring. So the idea is you could say the disk causes a torque which speeds up the ring. Simultaneously, the ring causes a torque which slows down the disk. And they're going to slide until their rotation rates match. And then at that point, they continue to rotate without slipping. Did that make some sense? So again, this thing's rotating, there's some sliding, they match RPMs, and then they rotate together. So there's 1 torques on 2, 2 torques on 1. Good enough?
Yeah.
Yep. All right. Other questions? I think that's cool. Is there anything practical you could think of that this relates to? There's not a lot of stick shifts anymore. So people might not view this, but imagine this as a clutch, right? You let up, right? Or you can have 2 discs friction coupled, which allows your car's transmission to engage different gears. You can pull these off and slide them on, and then, anyways, that kind of makes me think of that a little bit, but okay. Let's move on to neutron stars. Screw it. Oops, there we are. All right, I forgot to show people on Zoom. Whatever. It's a disc and a ring. Let's look at 11.6, will you? I'm going to erase the board. 11.6. This whiteboard's terrible today. One 1.6. Suppose we have a star, and it's initially rotating with a period of 30 days. And in this particular image, we're told it's rotating about this axis. We're told that the period of the star, 30 days. 30 days to complete 1 revolution. We're going to have this star collapses from radius initial equals 10 to the 4th kilometers to R final equals 3 kilometers. So if it helps, 10K is what? 6 miles, right? If you run a 10K, that's 6 miles. So this is what? 10, so that's 6,000 miles. Okay. So that's approximately, well, it's a little bigger than the radius of the Earth. The radius of the Earth is about 4,000 miles. 3 kilometers, that's about one Hancock College campus. So we're talking, and this could really happen. A star bigger than the Earth could collapse down to something the size of Allen Hancock College. That's mind-blowing. That's just crazy. All right, anyways, astronomy has got some crazy size scale issues. It's just mind-blowing. All right, so I cannot draw this to scale was the point of that, but I'm still going to try to draw some picture. So figure not to scale. It would be impossible for me to draw this to scale. All right. What do you think will happen to the star's rotation rate? What do you think? Will it stay the same? Will it increase or will it decrease? Increase. What do you think will happen to its energy, its rotational kinetic energy? Increase. Okay, why do you say increase? What's your thought process?
The rotation, if the rotation is increasing, then kinetic energy should also.
Usually you're right. And I think in this case, we'll show that you're correct. I like to think about it this way. Figure skater, arms out. Figure skater, arms in, right? You bring the mass close to the axis, you speed up. And then the other attribute, just a side note, I'm going to put it up here. We know the kinetic energy is 1/2 I omega squared. Usually what happens in these problems is the following. If I goes down, omega goes up, and vice versa. And they usually change by the same factor. So if your moment of inertia goes up by 3, your rotation rate goes down by 3. That's what we saw in the last problem. In this case, if your moment of inertia goes down by some crazy ass factor, your rotation rate is going to go up by some crazy ass factor. And because the rotation rate is squared, it's going to drive the energy change. So typically, but not always, if your omega goes up, your energy goes up. If your omega goes down, your energy goes down. Excellent. Good? All right. So we're going to expect this thing to rotate even faster. All right. Okay. Part A. What is the equation that relates period to angular frequency? Does anybody remember it? How does period relate to angular frequency? Or what's angular frequency? Do you even know what that is? It's the same thing as angular velocity. What symbol is angular velocity? Omega. So sometimes I'll call that angular frequency. So let's say omega, that's angular velocity. Sometimes it's angular speed, depending on the problem. Sometimes we call it angular frequency. Depending on the context of the problem, omega could mean any of these 3 things. They're all basically the same thing. Think RPM. It's something that relates to the RPM. Got it? What was the equation that relates omega to period? Do you remember? There was a 2 pi in it? Nope. It was 2 pi, I'll just tell you, over the period. We talked about this, I think, in chapter 6 very briefly. Do you remember that? Whatever, memorize that shit. Don't ever forget it, all right? We use that all the time. I don't know if that's on your equation sheet or not. I don't see it. Yeah. That's one that we use so often. I often tell students, you got to memorize it, never forget it. Let me write down the full version for you. Omega is 2 pi times the regular frequency, or 2 pi over the period. When you get your test handed to you, just scribble that down on there. Make sure you have that down. Okay, sorry it's not on the sheet. Memorize that. Yes.
Is that when alpha is constant? Or
No, this is true all the time.
Oh,
So at any instant in time, right? Now, I guess you're saying the period doesn't make sense, but you could get an average period and that would give you an average RPM.
oh,
You know what I'm saying?
yeah.
But generally speaking, I guess you're right. This is implying either average alpha or like some sort of on average, or alpha is 0. I see what you're saying. I like that clarification. Yeah. Generally speaking, we don't talk about the period of something unless that period is constant. Although here, we're deliberately changing the period, right? So yeah, it's a little bit goofy how that context might apply. And that's a very, subtle point. Good. All right. Now here's what I'd like to do. I want to show you the differences between this problem and the last problem. In the last problem, we had 2 objects and 1 final object, right? And notice there were 2 terms on this side and 1 term on that side. In this problem, the objects didn't change shape. So the moment of inertias remained constant. However, in this problem, do you agree the object is changing shape? So the moment of inertia is also going to have an initial and a final. So the way you write this crap down is this. Now think about that for a second. This is initial angular momentum, and this is final angular momentum. In this problem, we've got the z hat. We could put a negative k hat on here associated with the rotation vector, right? There's a negative k hat, but it's going to cancel out immediately. You agree? So that's why I oftentimes don't bother writing it. Okay, so far so good. Let's assume the star, I'm going to write this assumption down. We're going to make the assumption that the star is a uniform solid sphere. Clearly, stars are not going to have a uniform mass distribution, but we got to start this problem somewhere. So we're going to get an approximate idea of what's happening here, right? So that's fine. When we do this, what is the moment of inertia initial of this star? What's the general equation for the moment of inertia of this shape? Solid sphere. What page is that chart? 59? You might want to like dog ear page 59 in your book because we're going to be using it all day. 2/5 times m radius initial squared. And then the other one will be 2/5 mass radius final squared omega final, right? What drops out? Mass and the 2/5, the shape factor in this case. So notice, not only does the radius change, but we're going to get this crazy multiplier squared. We know stuff about the initial state. We could actually work this out for the final state, omega final is equal to, oops, omega initial times, what's it going to be? Radius initial. It's the radius ratio squared. Wait, did I flip it in that last one? I did. Sorry. So we could work this problem out and we could get the rotation rate. But wait a minute. Let's see what we're trying to figure out. Oh, I want to instead figure out the new period. So rather than do this problem with omegas, what we could do is actually rewrite this equation here in terms of the period. So I'm going to do that on this new board. Give me a second to erase. Give me a second. Still erasing. The board is terrible. Jeez, this is horrible. Better get this whole board erased. The other whiteboards on campus is this bad or no? You guys noticed?
It's hard to tell.
This one's just terrible. Oh, it's so bad. Whatever. All right, so we said I initial, omega initial. Why don't we use our cool new relationship? This is 2 pi over the period initial times 2 pi over the period final. So if we're going to work in terms of the period, we could rewrite this equation at the beginning in terms of the period. Notice the 2 pi's drop out, and we could relate the different periods. Which, if we solve this for the final period, what are we going to get here? Should be the initial period times some factor. Looks like it'll be I final over I initial. And just to kind of try and show you both at the same time. Whoops. Right? What I'm trying to do here is show you, you could do these problems in omega land or in period land. Okay, and you could do different, all right, so basically feel free to use that technique. If that's not exciting, I apologize. So this was actually part B. This is conservation of angular momentum in terms of the period. Well, if I plug in this particular result here, it's going to equal the initial period times 2/5 mass radius final squared over 2/5 mass radius initial squared. That's going to be radius final over radius initial quantity squared times the initial period. All right. So if I wanted to get the RPMs, I'd use this. If I want to use the period, we'll do this. Well, let's go ahead and punch in some numbers on this. Radius final was 3 kilometers. Radius initial was 10 to the 4th kilometers. We got to square that. Oh, and T initial was what? 30 days? So let's get this new period. It's actually kind of funny. Gonna get my calculator out. Three divided by 1 EE4, square that times 30. Let's see. Then I'm going to mode scientific. 2.7 times 10 to the minus 6 days is not a very convenient unit, right? So maybe what we could do is convert this into seconds. 1 day, 24 little hours, approximately. 1 hour, 3,600 seconds. When I punch that in, what do we get? Times 24 times 3,600. About 1/4 of a second. Think about that. You take a star that's rotating once every 30 days, and gravity causes this mass to collapse in on itself. Suddenly it's rotating 4 times a second. Now, believe it or not, maybe you've heard of things like pulsars, right? And so sometimes a star could be emitting a beam of radiation coming out of it. Maybe it could have some radio wave components. And the idea is it's spinning so fast, you see it as a blip on your telescope, pulsing. Tick, 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 tick. So this gives you an idea of what might be some of the physics involved in a pulsar. Hopefully that's kind of interesting. I don't know. All right. So far, so good. Let's get the change in energy now. So we need to do the change in energy again. Running out of room here. I guess we'll do it over there again. I'm going to write this up right here. T initial was 30 days. T final was, whoops, oh shoot, this was supposed to be T final here. I apologize. Got that information. I want to get the change in energy.
First of all, it's like an inverse of an explosion.
Yeah, yeah. It's a star collapse as opposed to like a supernova, right? Yeah. This time we're trying to get the fractional change, I believe. And I'm just trying to show you what that is. So it's without the percent, right? So basically you can think of this as a decimal and don't convert the percent. So this is the fractional change. Express your final answer as a fraction instead of a percent. I'm going to show you this trick too, right? Notice it's always going to be E final over E initial minus 1. Okay? All right. So delta K in this case is going to be the energy final is 1/2 I final omega final squared over 1/2 I initial. And then we're going to subtract the 1. The halves drop out. Remember, this is going to be 2/5 mR final squared. This is going to be 2/5 mR initial squared. Notice the 2/5 and the mass also drop out. Not the radius in this version. We get that result. And I'm going to cheat here. I want to show you something. Come on. That work we did at the beginning was not wasted time. Come on. Earlier, we did this problem with I omegas, and we figured out the final rotation rate in terms of the initial. And notice if we plug that in, I can get the omega initial to drop out too. So I'm going to do that. Omega final was this. And since it's squared in this term, you got to square both the omega initial, and this becomes to the 4th power, right? Oh, wait, I flipped it, didn't I? You see that? What did I screw up? This is initial over final. So right here, this should be initial over final. I screwed up. That's the numerator. And then we get what? I guess omega initials left on the bottom. So here's the R final over R initial squared. Here's the omega final squared. Here's the omega initial, and then there's a minus 1. So it's a little sloppy there. I apologize. Now, this term drops. 2 of these drop. 2 of those drop. That brings us back down to a squared. And we get this result. R initial squared over R final squared minus 1. And before we plug in any numbers, I want you to ask yourself, in this particular example, do you think this minus 1 is important? Numerically, is that going to make a big difference in this calculation? What's your gut say? I like that you don't just immediately jump to it. Help me out. What was R initial? A big number. It was 10 to the 4th kilometers. What was R final?
3 kilometers.
3 kilometers. When you plug in these numbers, the kilometers are going to cancel. You're going to get about 1,000, right? 3,300 or something like that, right? Then you're going to square it. Is that 1 important?
No.
No, not at all. So in some cases, you can kind of ignore this minus 1 and we get the final energy. So when you do this, it's basically 10 to the 4th over 3 squared. It's approximately equal to that because the -1 doesn't matter. You could punch in your calculator and get that. Oops. Divided by 3, x squared. It's basically 1 times 10 to the 11, or 1 point. I know I'm off the Zoom. I'll fix it in just a second. There we go. So notice the energy goes way up by about 10 million, a factor of 11 million. What causes the energy to go up? What's that? Right? You could do this without a star. You could do this with just a giant sphere and just compress the mass. Let me go to this whiteboard here. You got this star and it collapses down. What causes it to collapse? Gravity. You convert gravitational energy into kinetic. Could you do this problem with conservation of energy? Yes, but it's going to be really hard. Really hard, because you would have to account for the gravitational potential energy of each point mass in the star relative to each other point mass in the star. And you'd have to do a big calculus calculation. It's so much easier to use angular momentum for this problem, even though we could argue the energy is conserved if the gravitational energy is what makes it collapse. Yeah. All right. Anyways, kind of interesting, right? Go ahead.
Does delta K not have limits?
What do you think? Take a look at the original equation up here. He asked, does the delta K have units? What are the units of this term? Joules over joules. Yeah. So that's why we can express it as a fraction or a percent. It should be just a number. That's why I'm always doing these tricks to kind of cancel out as much as I can so I can actually get to a number. Even though we don't know the mass involved, we never knew the mass in this entire problem. You can still get a decimal number for some results. And that's kind of interesting. Cool? Yeah. Others? Let's do a demo real quick. You could look at 11.7 while I'm getting the demo set up. All right. This is the fun stuff. Go over here, check my Zoom camera real quick. Is there anybody that can do lots of spinning moves and not puke? Not get sick? I'm assuming it's okay. You want to try it, Robert? All right. Okay. There's some cool demos today. All right. So we're going to have you sit on this thing. And let me help you out here. I'm going to hold the stool at rest. You want to get your mass centered pretty close to the middle and put your feet up on there. All right. And then what I want to do is these. Do you agree that's fairly low friction bearings? You can see them slipping and sliding. So I'm going to put my foot on it for a second. What I want to do here is he's going to be our neutron star, right? So I want you to start with your arms out. Less talk, more rock. All you got to do is if you start getting sick, bring your arms out. So bring your arms in to your chest. It's crazy, right? And then bring them back out. So notice when he causes the star to collapse, he gets more rotational energy. Now in this case, here, let me pause this for a second. Good. No, you're good. So what I want to do here is I want to ask you, clearly his energy went up because his omega went up right? Obviously, the I went down, but it'll make a square. What was the source of the energy? How did he gain energy? Did it come out of nowhere? Where did the energy come from? Let's stick your arms out. Okay. He brings his arms in. Go ahead. He's increasing his speed. Where does the energy come from? This is not gravitational collapse. Go ahead and bring him out if you're going to get sick. What do you mean chemical energy? Yes, exactly. The Snickers bars, the bowl of Snickers bars and milk he ate for breakfast, the calories is being converted. So he's doing the work, not gravity. Let's give him a round of applause here. You guys want to try this out? We'll do that. As a side note, since we got the camera set up, can I look at this real quick? While we've got this set up before our break, could you do me a favor and look at page 90? And I need another volunteer. Somebody else that doesn't get sick. Thanks. Okay. Okay, so now, if you guys want, just come over and take a look at this. Go ahead, sit on the seat. Jules, is that still on Zoom?
Yeah, you're fine.
Okay, so now you're going to hold this like this. And then what I'm going to do is I'm going to give this some momentum with this Dremel. A lot of it. So don't press it in your face. Right? And then what I want you to do is you can, we're going to call this I guess, I don't know, what's not called it. But what you can do is you can twist your hands this way or that way. By doing this, he's going to change the angular momentum of the wheel. Right? What should happen to his angular momentum? If he increases the angular momentum of the wheel K hat, what should happen to his angular momentum? No. He's going to exert a torque on the wheel, so the wheel must exert a torque on him and rotate him the other way. Then if you want the super boost, you start here and go all the way. You know what I'm saying? All right, let's see this. Oh, sorry, I gotta do this way. Oh no. Crap, I burned out the battery. Let's go the other one. That's why you want backup Dremel. We'll just go on the same way. Not my day, is it? All right, I'm going old fashioned. Sorry. Ready? Okay, go for it. Try flipping it the other way. Then hold it vertical again. Notice, I forget which way it's rotating. Let me stop and do this again. Okay, so I'm going to whip this thing down, right? So as a result, when he turns it this way, it's going to be rotating like this. That's going to have angular momentum downwards, so he should have angular momentum upwards, right? So let's walk this through. If I whip this down, he rotates it this way. The wheel is now rotating this way. He should rotate the other way. Got it? Let's see if this happens. All right. I forget what way I said.
Yeah, that way.
Did it work?
Yes. Yeah.
Now flip it the other way. All right, and now go ahead and bring it straight up, or flip it all the way to one side. Now do the double flip. He's changed, now go all the way over. He should get twice as much change this direction, right? Pretty cool. And then as a weird side note, all right, let's give him a round of applause here. Grab a rope real quick. Sorry, the Dremel didn't work there. Usually with the Dremel, we get massive amounts of right.
The battery's charged for its signal speeds.
What's that?
If the battery stays charged or it stays.
Or if it's, yeah, 2 Dremels is not enough. I need 5, I guess. Yeah, right? Let's do this. Go ahead and get that out of there. Just stand up. This is a weird one too. Over here. Right about there. Here's the camera. The idea is you're going to hold this string. And then about right there, you kind of go grab all this extra string. Please. Try and grab this big ball of crap. Got it? And then go ahead and push that. Now what I'm going to do is I'm going to give this thing a lot of angular momentum and let go. Oh, sorry. This class is full of wonder, isn't it? Isn't this a weird one? What are the forces acting on the wheel right now? What's one force acting on the wheel? Tension from the cable. What else? Gravity. Oops, sorry, on that. And there's some air resistance. Let's assume that's negligible. This is going to fall over. So give me a second. Yeah, it hurts. Why doesn't the wheel fall down? This is like a top. This has to do with precessional motion. It's beyond the scope of our course, but it is mentioned on page.
It's 91.
91. Page 91 talks about this. If you want to learn more, we can discuss it later. It's a really cool physics phenomenon. Okay, let's give him a round of applause here. Thank you. Thank you. So yeah, go ahead. If you're interested in this and you want to check it out over the break, you can actually feel it and balance it. And obviously, the faster it's rotating, the more angular momentum it has, the harder it is for gravity to change the angular momentum. Right? The gravity causes a torque, and that changes the angular momentum. And it turns out it's changing the angular momentum direction. We don't really cover that in this class, but if you want to learn more, talk to me after. Let's take a short break and we'll come back and do more problems. Oh man, it's been that kind of day already, huh? Thanks. Okay. How's the pacing today? Am I going too slow or is this about right?
It's about right.
Okay, all right. Remember, you could rush ahead. My goal here is to kind of try and show you one of each problem that might appear on a test. Notice we've seen spinning objects that collide. That was 10.5. We did a spinning object changing shape. That was 11.6. Now I want to do point mass hits a rod. We alluded to this last time and I kind of sketched it out, but let's do 11.8. 11.8. And read the note at the top of page 87. Drives me freaking nuts. We spend a week on this and then everybody uses conservation of energy inappropriately. We're going to have a ceiling here, pivot, and some rod. And then there's a point mass moving with some speed v. This is stage 1. Stage 2. Impact. Stage 3. Swings up to max angle. There's some max angle. I think I just called it theta or whatever. Give you a visual. Give me a sec, just a second. I know this seems a bit contrived here, but I've got this meter stick. There's some Velcro here. You can imagine I throw this ball, right? I'm going to throw the ball. It's going to impact the meter stick. It's going to stick, and then it's going to swing up to some maximum angle. Got it? Now we'll do the experiment in a minute. But again, somehow this ball is going to hit this thing and swing upwards. All right? Oops. So at the end of this one, we'll run the math and see if it matches reality. What is the mass of the point mass? It says it has mass m. And then the rod has mass 2m. Okay. This particular rod has length d. And a lot of your exam questions are going to be written like this, where the masses have basically, they're almost identical to your homework, but I changed the numbers here. Like I could say 2d or 4m or 2m or something like that, or m over 2, right? So I really want you to get used to this experience of solving these problems algebraically, since that's how I test you. Our goal is to figure out that final angle. That's our goal, is to figure out theta. And I guess I should be clear here. I want to specify that impact has happened right here. And this is now rotating. So this is just after impact. And this would be just before impact. And that's critical that we get this clear, right? This is just before impact. This is just after when it's rotating. All right. We've got stage 1, 2, and 3. When is it appropriate to use conservation of angular momentum? Not necessarily. Now, to be fair, you could, if you can always use it, as long as you consider all sources of angular momentum in the universe. But sometimes that could be very tedious, right? And sometimes it's hard to measure all those. In particular, this is one of those cases. So let me rephrase. Let me start over. We have 3 stages here, 1, 2, and 3. Usually, I don't know if you've noticed this in physics, we usually take 2 pictures and write an equation that compares the before to the after state. So we're going to do that for stage 1 and 2. And then we're going to do it again for stage 2 and 3. And what my question is, between stages 1 and 2, is angular momentum conserved? And between stages 2 and 3, is angular momentum conserved? And I think I specifically stated, no, I didn't. All right, so I'm going to leave that out. What do you think? In particular, let's go with your comment. Is there angular momentum at the max angle? How fast is it rotating when it gets to the maximum? It's not. So is there angular momentum over here? Is there angular momentum right here? Yeah, it's rotating. Is angular momentum conserved between 2 and 3? Is it the same in 2 and 3?
No.
Absolutely not. So we would not want to use angular momentum here.
So 1 and 3.
Is there angular momentum here? Yes. Point particles moving in a straight line have mvr perp. So there is angular momentum here. There is angular momentum here. There isn't here. Now, to be clear, obviously there's angular momentum all the time because the Earth is rotating, but we're kind of ignoring that. The reason we don't see angular momentum conserved between 2 and 3 is this swinging rod is bolted to a ceiling, which is connected to the floor. And as this one stops rotation, we change the Earth's rotation. But it's not by any amount you could measure or visualize. So even though angular momentum is conserved here, we can't quantify the Earth's change in angular momentum because it's so minuscule, we'd never be able to measure it. So we say angular momentum is not conserved for the rod-clay system. It is conserved in the entire universe, but that doesn't help. And that's where I was going with that earlier. Does that make sense why I'm babbling? How about you guys feeling okay with that? So in short, part A, angumom conserved between stages 1 and 2, not 1 and 3, or 2 and 3. Got it? And to be clear, we're assuming the rod clay system. Part B. Oh, what's the reasoning? What has to be 0 for angular momentum to be conserved? Sum of well, what are the forces? Here's the rod. What is one force acting on the rod during the collision? I guess there's the ball here too, right? During collision. What is one force that acts on the rod? What's always there?
Yeah.
Gravity. What's another force? Is there a force on the rod from the ball? Yeah. Force of ball on rod. Is there a force from the rod on the ball? Is the rod exerting a force on the ball?
Yep.
Yeah, Newton's third law. There's a force of the rod on the ball. What's true about this force in this system? It's internal. 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 So I don't need to worry about that. Are there any other forces? The thing holding it, the pivot point. Which way does the pivot point exert a force? I know you're tired. This is important. Which way does the pivot point exert a force? Up. I'm going to call that R subscript Y. But that's not all. It exerts a force another direction too. When I punch this meter stick, watch the top of the meter stick. Maybe I'll get an arrow so you can see it better. I'll punch it in slow motion. Ah, there's one right there. Take a look at this arrow. Right? There's a pivot point right here. When I punch this, notice this top of the arrow doesn't move, right? But when I punch it without that pivot point, look which way the tip of the arrow goes. I'm trying to let go right as I punch it. Do you notice the tip of the arrow coming towards me? So when there's no pivot point, the arrow comes towards me. When there is a pivot point, it doesn't move that way. What direction is the force at the top? It's opposing this collision. So it's not just upwards. Got it? This is crucial. I know you're tired, but you've got to understand that. The pivot point will oppose the impact, and it's going to depend on where you hit this thing, right? If you hit it here, above the center of gravity, the force is actually pointed the other way, but we'll discuss that later. Right? If you punch it up top, watch the tip of the arrow, right? So the pivot point would serve to hold it back this way. So it could change, right? But Rx is either going to be to the left or to the right during the collision, unless you hit it at the sweet spot. Do these forces cause torques? Here's my pivot point. Do Rx or Ry cause a torque? No. Their lines of action are through the pivot. You agree this one has a line of action through the pivot? And so does this one. What about mg? Is the line of action for mg through the pivot point? Yes. As long as the collision takes a very short amount of time, now to be fair, you might be saying no because technically it's going to be angled a little bit. Right? During the collision, right, you might be saying, well, part of the time the board is actually angled a little bit. And if the board is angled, notice the mg is slightly off axis from the pivot point. However, if the collision happens in a short amount of time, the line of action for mg is approximately through the pivot point. And so that's, is that good on that? It's not strictly through the pivot point for the entire collision, but as long as collision time is short, it's not through the pivot point exactly, but it's approximately through pivot. Therefore, sum of torques is approximately 0. Good enough? Yes?
Is that why in stage 3 it's not? It's like the sum of torques is something?
Exactly. So notice here, gravity is causing a torque. Do you agree in this stage? Look at it. mg is right here at the, well, it's at the center of mass, which is probably a little bit down low, right?
Yeah.
So in this case, and it would be m total, clearly it's causing a torque at this point, and that's what's chewing up the angular momentum. It's taking it from some angular momentum and slowing it down. So the gravity is the external force that's reducing the torque to 0, or sorry, reducing the angular momentum to 0. Cool? All right. Part C. When can we use conservation of energy? In particular, can I use conservation of energy between stages 1 and 2? What do you think? No. How do you know?
So
That's right. So we have a perfectly inelastic collision. E1 is greater than E2. We're going to lose some energy. So that's part C, or that's part of it. How about between stage 2 and 3? Is energy conserved between stages 2 and 3? What do you think? I know this seems like we're spending a lot of time on it, but right, you've got to get this right or you get the wrong equation and then you get the wrong answer every time. In stage 2 and 3, what type of energy do we have initial? Okay, what type of energy do we have final?
Potential.
Okay, is there going to be any work done? We're probably going to ignore friction, right? And air resistance. What about these forces? Are these forces going to do any work?
Yes.
Which ones? Gravity. But we can account for that with conservative. It's a conservative force, so we can account for that with energy. These forces at the pivot, there's no displacement. They do no work. So E2 does equal E3. Only work is done by mg, a conservative force. Does that make any sense? Sorry about that. So that's part D. Right, gravity is the only force that's going to do work. Since that's a conservative force, we can just do energy problem. Right? It's work external non-conservative. Well, this is a conservative. What about momentum? When I say momentum, I do not mean angular momentum. I mean translational or linear momentum. What do you think? Just a bonus question. I mean, this question is probably on your final exam. Which conservation laws apply? I'd put it on every final exam ever. Just to see if you know when these, right? So we got to get this right. Do you think momentum is conserved here? Linear momentum, P. What is the rule for linear momentum? Right? So for energy, work external has to be 0. For angular momentum, torque external had to be 0. What was it for momentum? Linear momentum. Force external. Is there 0 external force? What's that? Ry and mg are going to balance, right? And I guess technically speaking, shouldn't I also put mass of the ball in this picture here too? Right? Because if we're talking about the rod and the piece of clay as a system, we need to have both mg's. Sorry about that. Ry should be balancing these two out, right?
And the other two are internal. So
These two are internal, So what do you think? Is the linear momentum conserved?
Yes.
No,
No. Oh.
that one's not balanced. You see it? Isn't that interesting? So what happens is this force on the rod is not balanced. And so when you do this problem, angular momentum is conserved, but not linear because of the pivot. If we had done this in free space, like this, if I had just taken this meter stick and punched it, then both would be conserved. Right? Because there's no pivot to hold it back. So typically on your final exam, you're either going to have a pivot or not, and you have to know that the pivot prevents linear momentum from being conserved. Got that? Ready to do the problem? Where'd that meter stick go? Oh my gosh, it's like through the door. Okay, whatever. I'm trying to go slow and not confuse you, but maybe I'm just slow and confusing today. I apologize. All right. Why does the center of mass matter in this problem? So if you're doing a torque problem, you need to know where gravity acts, or if you're doing an MGH, you need to use the height of the center of mass. All right. So here we go. I'm going to redraw these pictures really quick. We need to know the height of the center of mass here, so that when it rotates, we can understand how high the mass went. That's the main idea. Did that make sense of it? Okay. Between stage 1 and 2, what rule am I supposed to apply? Conservation of energy, conservation of linear momentum, or conservation of angular momentum? Angular momentum. L initial equals L final. What's the initial angular momentum? You've got the rod is not moving. What has the initial angular momentum? The point mass, the ball. What is the equation for angular momentum of a point particle? What was the shortcut trick we were supposed to use? R perp, which is this impact parameter. What's the final moment of inertia? Or sorry, the final angular momentum? What's a good way to write the final angular momentum if you have this weird object rotating with some rate omega? I omega. What is I? Now wait, I want to make sure I get the right masses. The ball had mass M. Okay. Okay, got it. What's the moment of inertia? In this case, what's one object that's rotating? The rod. What's the moment of inertia of the rod? Is it 1/12 or 1/3? What is a rod about? Which one's got to be bigger? 1/12 is the center. Where is this thing rotating?
Oh, yeah.
Yeah. So I need 1/3 The mass is now 2m. The length is d, so length squared. What about the point mass? What's the moment of inertia of the point mass in this case? How far is it from the pivot? L, or in this case, notice what I start to do now is I start to call the length of rods d so that I don't get confused with angular momentum L and length of rod L. So I try to do that in this chapter. I change all the lengths to d's. So it's d. And so this is just mass of the point mass, which was m, d squared. And I'll get n omega, right? What is r perpendicular for this problem? I draw the line of motion. What's the distance to the line of motion? D. So r perpendicular is D. Notice what is unknown in this equation. In the problem, we were given the masses, D and V. Yeah, omega can be determined. Agree? Let's get it. Oh man, wouldn't it make sense to kind of clean this up a little bit? This is going to be 2/3 md squared plus md squared. Isn't that 5/3 md squared? Double check that for me. Is that right? 2/3 plus 3/3. Yeah, I think that's right. Notice what's going to cancel. One of the d's. And so we get omega. You can do this on your paper. I'm going to try and do it in my head because I'm running out of room. Always dangerous. I think that 5/3 is going to flip, and I'll get 3v over 5d, which has the right units. Meters per second divided by meters is radians per second. Is that what you got? 3d over 5d for omega? Okay. So now we know the rotation rate. Now we can plug that into the energy equation. I could say stage 2 to 3. We've already discussed that the work was 0. So now I can just plug it in. It's 1/2 I omega squared has got to equal mg height of the center of mass. And here I got to be careful. I got to use the total mass. I, we just figured out, was 5/3. So this is going to be 1/2 times 5/3 md squared times omega squared, which was 3v over 5d. And we're going to square that. See that? Mass total is how much? What's the total amount of mass? 3m, because there's a rod of mass 2m and a point mass m. It's not 2m, it's 3m. So far, so good? G, what's the height of the center of mass for an object that swings up like this? Do you remember that? So if we could just figure out the radius of the center mass, we're golden. Do you agree? Well, let's figure that out. So the radius for the rod is going to be d over 2. The radius for object 2, the point mass, is going to be d, the entire length of the rod. So the radius for the center of mass should equal mass 1 radius 1 plus mass 2 radius. What? The radius of the center mass is, what's mass 1 in this case? What is object 1 in this picture?
Wait, no, not.
I should, yeah. Boy, I probably screwed up. I should have called this one radius 1, right? Because that's mass 1. But in this case, radius 1 is for the rod, which has mass 2m. Ah! Right? Do you agree? Radius 1 represents the rod center mass. Its mass is 2m. Plus this one, mass 2 is the point mass, which has mass m. Radius 2 is the full d. Notice the radius to the center mass is equal to what? D over 3? How convenient. This is D over 3. So now we got to not screw up the algebra. Let's take our time here and try to see what's going to cancel out. In particular, does the mass drop out? Mass is to the first power. Will the D drop out? On this side it will, right? I have a D squared, that's going to take care of this D. Is the V going to drop out? No. Okay, that's fine. What about the 3? That's going to drop. And now I'm starting to get lost. I'm going to just rewrite because I'm getting lost. I get 1/2 times 5/3 times 3 squared over 5 squared times V squared equals G D 1 minus cosine theta. What are we trying to find? What was the goal of this problem? Do you remember? Are we going to be able to do it? V was a given, G is a given, D is a given. Okay, let's clean this up. Now I can see that one of these 3's cancels, one of these 5 cancels, and it looks like I get what, 3 over 10 or something like that? Wait a minute, I screwed up something here, didn't I? What was this calculation right here? It's not D over 3. 2D. Yeah. Do you see that? There's an M and an M. I scratched off too many 2's. I made a mistake. That should make this 2D over 3, which means there's still a 2 right here. So after all that rearranging, I'm going to get 1 minus cosine theta is equal to, oh my gosh, 3 V squared all over 20 GD. And out of all that, you get theta equals cosine inverse of 1 minus that junk. Do a little algebra there. What should we check? Units. Do you agree this is crazy? You want to constantly check your units. What are the units of V squared? Meter square second squared. What are the units of this thing? Meter squared second squared. Oh crap, that's sweet. Yeah, because it's meters per second squared times, yeah, you're right. Meters squared per second squared, no units. And that's what it should be. What do you think?
So stage 1 to 2, we did a conservation of angular momentum type. And then stage 2 to 3, we did conservation of energy.
Correct. And the whole point was, you on test day, this is a very common question either on test 3 or the final or both. You're supposed to be able to recognize when is it okay to use these different techniques, right? And so if it helps, maybe a little, I personally like to see this, right? So I apologize if I'm wasting your time, but I'm just going to set this up. Give me just a second on Zoom, people. Okay. Okay. Almost there. Just setting it up. Let me switch the camera over so you can see what I'm doing. How about that? Whoops, wrong one. Okay. Then, you want to help me out again?
Yeah.
Then let me get my big protractor. So the idea here, hopefully you can hold this. Actually, I'll hold this in the green screen, and you're gonna get this. You want to set it right in the groove there. Actually, yeah, you're gonna get there, and then just try and line it up right in the groove. Got it? Right, and then give me just a sec. This is crazy, but yeah. All right. Jules, is this on the screen at all?
Yeah.
Sweet, because I can't move at this point. Okay, go ahead and let it rip. And so you can see that goes up to a maximum angle of about right there, which is about 25 degrees, right? So now keep in mind, we don't know the initial speed of this ball, right? But couldn't we do a rolling motion energy problem? We know the initial height, figure out the V initial, then figure out, oh my God, you see what I'm saying? It's just putting all the pieces together. So if you wanted to do this at home, let's do a quick height measurement. Where's that meter stick I threw and smashed? Here it is. Somehow it went all the way through. Oh, and I broke it. But the idea is, just approximately, it's about 26 centimeters up in the air. So if you wanted to, you could do an energy problem like this. Let's give our assistant a round of applause there. So if we wanted to actually do this, we saw that theta max, what did I say it was, about 25 degrees?
Yeah.
Right? Plus or minus maybe 5 degrees. And then what we could do is we say, we started out with height initial was 26 centimeters. And then for this one, I think we've got the masses of these things. So the meter stick is 77 grams, and this one is, let me just check real quick. Making sure these masses are about right. Come on. And the golf ball is about 46. So it's not exactly 2-to-1 ratio, but it's pretty close. So M is about 40 grams, plus or minus, say, 6 grams. And then 2M fits in there too. So if you wanted to do this, right, remember we discovered the energy problem for this was mgh equals 1/2 mv squared plus 1/2 I omega squared, which then we said this was 1/2 mv squared plus 1/2, this is a golf ball, so it's 2/5 mr squared omega, which notice this cancels, and we get mgh equals 1/2 plus 1/5 mv squared, then you could use this calculation to get v equals the square root of, let's see, what is that? 1/2 plus 1/5. Well, we could do tenths, so 5/10 plus 2/10, that's 7/10. That's going to be 10/7 GH or something like that. You could double check this. I'll put a question mark there. So if you have 26 centimeters, you can convert the units, plug it in, that gives you V. You can do all the math and solve this problem. Oh, that hurts. Right on the knuckle of my toe. Yeah. I guess I was doing that one a little faster than the others today, huh? Oh my goodness. It's about time to go. We've got 5 minutes, so I want to kind of summarize some things. While you guys are writing that up, I'm going to make some space here. Make a few notes. There's never enough time, right? So let me go over here. Come on. Right? So let me see, there's another problem here. Specify. .6. So if you redo the problems that we did today at home, plus these problems, and to be clear, this one's super freaking hard, but it's not hard because the concept is difficult. It's hard from a standpoint of paying attention to detail. Right? No single step is that hard in any of these, but there's a lot of steps. Do you agree? And so there's a lot of spots to screw up, a lot of spots to accidentally plug in M instead of 2M, or D instead of 2D, or D/2. So you need to do enough of these so that you're used to the process of plugging in the right symbol and making your screw ups on homework instead of on test day. So if you do those, that's great. And if you have the chance, look at page 93 really quick. There's a summary written on page 93. On page 93, I mentioned the 3 conditions that I've been hammering today. When can you use conservation of momentum? When can you use conservation of angular momentum? When can you use conservation of energy? All right. And now when you look at this, pages 93 to 97 look horrible. You're like, that looks like bigger than any side. But if you look carefully at those questions, what I'm trying to do there is just say, which conservation laws apply? So what I did is I gave you a bunch of problems that look like test questions. So you could just look at those and say, which conservation laws apply here? And then you can look at the answer and see if you got it right. So it's a way to quickly practice, do you know how to get the right questions? Does that make sense? So, right, you got to be good at that. Otherwise, you're going to apply. Once you get to the equations, it's easy. It's getting the right equations. As a side note, I really love problem 11.16. And I think you guys could probably figure this out and do this. One of the things, I usually do that one in class, but with Zoom, I'm a little slower than usual. I'm not going to do it this time. All of these questions are straight from textbooks that are used at MIT, Harvard, Stanford, all the best schools, right? At this point, maybe not when you started this class, but at this point, you are just as good as anybody at any school, anywhere, if you just work at it. Right? People from Hancock have gone to Stanford, to Berkeley, to UCLA, to Cornell, all over the world. They're working for NASA. It's easy to think, oh, I'm not as good as them. That's a bunch of shit. You guys are just as good as these people. I want you to go out there and destroy them. So I want you to be aware at this point, you're doing difficult, complicated technical calculations as well as the best students in the world. You just keep working at it, keep practicing, and hopefully you can shake some of that inferiority. You're like, oh, this is just Hancock. Don't say that anymore, right? You're like, I can do physics. You just got to practice. Got it? And now I need a volunteer, just for a fun one at the end. I need somebody that's got a strong rotator cuff. Give me a second. Let's just have a good time. Whoops, not this one. This is a student demo. A student built this thing. I've got this suitcase. I need somebody to carry this suitcase, take 3 steps forward, turn right. That's it. Okay. Oh, but before you do that, I swear there's nothing special here. No. Give me a second. Don't look. Perfectly normal suitcase here. There we go. Perfectly normal suitcase. Jules, are we on the screen?
Yep.
Thanks. Nothing up my sleeve. Perfectly normal suitcase. All right. Hurry before it stops. Try to walk forwards and turn. Now turn. Notice that. Gee. Sorry that demo's kind of lame, but let's look what's inside the suitcase here. Yes, there's a giant. So what I did is I told some student it would be really cool to have this. Look at this crazy thing. Oh my God. That's a 45-pound weight. And when you get enough angular momentum on it, it's just like the magic wheel. It's really difficult to turn. So if you want to try this out, we'll try to do that. Anyways, let's go ahead and stop the live stream there and call it a day. This is some problem in there called secret suitcase. Does anybody see it in the workbook? I think it's on the. Secret suitcase. Where is that damn thing? Oh, 11.14 if you want to see it more. All right, I'm going to stop the live stream there. Angular momentum is just fun.